Hi Math 60. In this video we're going to introduce the idea of the real number system. This is section 1.3. So before we consider actual types of numbers, what we need to do is consider the idea of what's called a set. A set is just a collection of objects whose contents can be clearly determined. So it's just a collection of things, right? So a set could be your collection of model airplanes or your collection of colored pencils or something like that. It's just a collection of objects. The objects in the set are called elements of the set. We can do this for numbers also. We can have sets of numbers. And so, for example, we can use the set of numbers used for counting. This would be the set of numbers 1, 2, 3, 4, 5. And the little three dots here represent that the set continues on in the same pattern. So, for example, 6, 7, 8, 9, and 10, and so forth would be continuing on for the set. The squiggly braces that are right here, the squiggly brackets that are right here, indicate the notion or idea of a set, right? It means a collection of objects. So that those squiggly brackets there are specifically used only to represent a set, just to represent a collection of objects. Okay, this form we use right here with the commas just indicates the elements being separated from each other, right? So we put a little comma between 1 and 2 to say that 1 and 2 are both elements of the set. All right, yet let's use this idea of the set now to talk about kinds of, oops, sorry about that, I went back a slide. Let's talk about kinds of numbers. So the set of counting numbers is also called the set of natural numbers. And so this is the set 1, 2, 3, 4, 5. This is just the natural number system, the ones that are the most intuitive, the ones that were the first arrived upon when numbers were first being thought about, right? These are the easiest ones to think about. You have 1 sheep, you have 2 sheep, you have 3 sheep, you have that kind of stuff. Okay, the next number set is when we include the idea of the number 0. This one didn't come first, so in terms of historical content here, the natural numbers came first, then the set of whole numbers, because it was kind of difficult to think about what the number 0 actually meant here. So this set came second, and that's kind of an easy way to remember these two as well. Natural numbers come first, and the whole numbers, which include 0, right, it's the natural numbers plus 0, they came next. But there are lots of situations where this, if we just considered this number set right here, that's not good enough. For example, a temperature below 0, right? We've heard about negative temperatures, or if you've overdrawn your checking account. So what we need is to have numbers that denote owing something or being on the other side of 0, technically. That number set is considered the integers. This set contains all of the natural numbers, 1, 2, 3, 4, 5, and on, the whole numbers, 0, 1, 2, 3, 4, 5, and on, but also the corresponding negatives of the natural numbers. So negative 1, negative 2, negative 3, negative 4, negative 5, correct? And you can kind of think of it in terms of like how far away something is from 0, right? 1 is 1 unit away from 0, going in the positive direction, sort of moving that way away from 0. And this one right here is 1 unit away from 0, but moving left, right? So on the left side of 0. So we can use these kinds of numbers here to denote things from everyday life. So for example, owing a debt of $34, you can write that as the number negative 34. Okay, so let's see. We can actually use a visual representation to denote these number sets that we've been coming up with. So we can use what's called a number line, and this is a graph we will use to visualize the set of integers as well as other sets of numbers. So the number line extends indefinitely in both directions. It's a horizontal line as drawn below. 0 separates the positive numbers that are over here on the right from the negative numbers that are on the left. Okay, the positive integers are located on the right of 0 and the negative integers are located to the left of 0. 0 is not considered either a positive or a negative number. And the tick marks that are labeled here tell you how far away that tick mark is from 0. So the reason 2 is located at this tick mark is because it is 1, 2 units away from 0 in the positive direction, right? And also something interesting to notice is that for every positive integer here on the number line, there is a coordinating negative integer just as far away, but in the opposite direction of 0 as positive 2 is, right? So 2 is over here, negative 2 is just as far away from 0, but in the opposite direction. This will also be true for even more numbers that we will talk about in other classes, but this is also true specifically for the real numbers. Okay. So let's see, this is 6. So this is just a uh, summary here of the numbers that we have come up with in our little talk together here today. So we have the natural numbers, the whole numbers, integers. We'll be talking about rationals, irrationals, and real in just a second. But so far we have the naturals are 1, 2, 3, 4 counting numbers, whole numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, keep going. The integers are the whole numbers with the corresponding negatives. Okay, and remember that the little ellipses means to keep going. All right. So let's talk about the rational numbers. So the rational number specifically is basically going to consist of the fractions, but we call them rational numbers instead, right? So this is the set of all the numbers that can be expressed in the form a over b, right? This is like a fraction written sideways like this. Sometimes you'll see it as a over b with the little slash like this, right? What's interesting though and important is that a and b are integers, which means they can be positive or negative, and the denominator here, this 4, where the 4 is sitting right now, where that b is, that can't be 0, okay? Because division by 0 is not defined. In decimal form for these rational numbers, each rational number terminates. So for example, 0.25 represents a rational number. Its fraction equivalent is 1/4. Or it could also repeat in a block. What that means is you might have a repeating decimal like this. This actual decimal right here, 0.3 repeating, that is 1/3. Okay, each of these shown is a rational number. All right, let's see, what else? Let's talk about irrational numbers. The set of irrational numbers is the set of numbers that are not rational. That's the easiest way to define them, but there's another way. So the decimal representation is neither terminating nor repeating. So 1/3, 1/4, those are not examples of irrational numbers because their decimals terminate or repeat. Okay, irrational numbers cannot be expressed as a quotient of integers. That's a fancy way of saying you can't write them as a fraction. Right? And each of these numbers listed below are irrational numbers. You may have seen this symbol before. This is the symbol for the number pi. This is 3.1415926, blah, 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 blah. It keeps going on and on and on. The decimal does not terminate or repeat. The square root of 3 is also irrational. And so is the square root of 2. And if the square root of 2 is irrational, then so is the negative square root of 2. Again, their decimals do not repeat and do not terminate. All right, let's finally consider the real numbers. So all numbers that can be represented by points on the number line are called real numbers. The set of real numbers is formed by combining the rationals and irrationals. So if you take the rational numbers, all the fractions, all the decimals that are terminating and not and or repeating, and the irrational numbers, the decimals that are not terminating and not repeating, and smush them all together into one big set, you will get the real numbers. Okay, so we say the real numbers is technically the union of the rationals and the irrationals. So every real number is either rational or irrational since the reals are made up of the rationals and the irrationals. Okay, and every real number also has a place on the number line. Whether we label it or not, that's a different story, but it's there, right? So we may not label where pi is on the number line, but it has a position on the number line. We may not label where 1/3 is, but it has a position on the number line. That one's easier to label than where pi is, okay? But every single number, real number, is going to have a position on the number line. Okay, so last thing for this section is to consider what's called absolute value. Absolute value is used to describe how to operate with the positive and negative numbers. So there's a geometric meaning to absolute value. The absolute value of a real number, again, so this is a real number. It can be positive, negative, rational, irrational, integer, whole number, it can be anything. We denote the absolute value notation with these vertical bars like this. What this represents is how far that number A is away from 0 on the number line. And distance is always non-negative. It's always a positive number. So for example, if I wanted the absolute value of -5, well, how far away is -5 from 0? Well, remember that -5 is 5 units to the left of 0 on the number line. So it is 5 units away from 0. So notice this is the answer to the absolute value is +5 because it's 5 units away from 0. Alternatively, what if I wanted the absolute value of 3? Well, 3 is a real number. It is 3 units to the right of 0 on the number line because this is a +3. So the distance from 0 is 3. So notice that for a positive number, the absolute value doesn't do anything. It just returns the same number. But for a negative number, it returns the same number with the opposite sign. That ends our sort of introduction to section 1.3 on to 1.4.